Hello. In this video, I'm just going to go through several of the examples that were in the last lecture on stoichiometry. If you have not yet, I highly encourage you to do these on your own first. Try them, see if you can come up with the right answers. If you can, great, you're all set. But if you were struggling with these as you attempted them on your own, then I'm going to walk you through the process here of how you would do these problems. And so the first one that we encounter is a reaction between SiO2 and carbon to form silicon carbide and carbon monoxide. And so we want to first find the limiting reactant, or we need to first find the limiting reactant in order to then go on to find our theoretical yield. And so the first thing that should sort of strike you about this equation is that it's not balanced. And so that's the first thing that we really want to do. And so let's go ahead and write this equation out and then balance it. And so we have SiO2. I'm just going to leave the states of matter off for now because they don't really matter for what we're doing. Plus carbon forms our silicon carbide and carbon monoxide. Now we see that in order to balance this equation, we have two oxygens over in our reactant side, but only one over in our product side. And so we can fix that by having two carbon monoxides. That now gives us two carbons in our product side. So we're going to fix that by putting a 2 in front of our carbon in the reactant side. So now we have a correctly balanced equation. The next step is to convert each of the given amounts over into moles. And so we start with 5.00 grams of our SiO2, 5.00 times 10 to the third. That's a very important piece here, Professor Staples. So 5.00 times 10 to the third grams of silicon dioxide. And we're going to just simply convert that over to moles. So we'll use the molar mass of silicon dioxide of 60.08. And we do this out using my trusty calculator. And we have a value of 83.22 moles of SiO2. And now we do the same thing for our other given amount, for carbon. 5.00 times 10 to the third grams of carbon. Molar mass of carbon is 12.01 grams per mole. And so we have a molar amount of 416.3 moles of carbon. So the next thing to do is to compare the molar ratios of what we have compared to the molar ratios of what we need from our balanced chemical equation. So the way that I typically do this is I just divide so that I end up with a whole number. So again, it doesn't matter which way you divide, which you divide by which, as long as you do stay consistent. I just usually place the larger number over the smaller one. And so I see that I'm going to need 400, or that I have 416.3 moles of carbon to every 83.2 moles of SiO2. And so what I have is 5. Let me just write that a little different so it's in the ratio. Here we go. I have 5 moles of carbon to every 1 mole of SiO2. So that's just the ratio of moles that I have to begin with from my starting amounts. I have 5 moles of carbon to every 1 mole of silicon dioxide. And so this is what I have. We can go back and look at our balanced chemical equation to see that what I need is 2 moles of carbon to every 1 mole of SiO2. And so that's how much I actually need. And I just got that from my balanced chemical equation. So then we can compare those two molar ratios. I have 5 moles of carbon to every mole of silicon dioxide. I only need 2 moles of carbon to every mole of silicon dioxide. So I can see that I have a lot more carbon than what is actually needed. That tells me that carbon is in excess. I have more than enough carbon compared to what I actually need. Therefore, the silicon dioxide is clearly what limits this reaction. Sorry, I'm not sure why that's writing in gray. Oh, still is. Now I know why. There we go. Technology's getting the better of me this morning. So my SiO2 limits the reaction. And so now I can just take that the rest of the way out. I know that that the SiO2 limits, and so I'm going to start from my 83.22 moles of the SiO2. I'm looking eventually for my silicon carbide. That's what I'm asked for in the problem. And so I'm going to go ahead and do my molar ratio of 1 mole of silicon carbide per every 1 mole of SiO2. And then lastly, I'm looking for the theoretical yield, and that's typically going to be in grams of my silicon carbide. And so I'm going to then use the molar mass of silicon carbide, which I haven't looked up yet, but silicon 28.0855. I knew it would be handy to have a periodic table backdrop, plus my carbon of 12.01. So a molar mass of 40.0955 grams per mole. And then I do that math out. I get 83.22 times 1 divided by 1, but then times 40.0955 for 3,336.74. I want to round that off for my sig figs. I was given 3 significant digits to start. And so I'm going to round this, and I might as well put it in scientific notation, to 3.34 times 10 to the 3rd grams of silicon carbide for my final answer. Let's see if that matches up with what we had to begin with. Sure enough, 3.34 times 10 to the 3rd grams of silicon carbide. So again, we're comparing our molar ratios of what we actually have to start compared to what we actually need, which we get from our balanced chemical equation. Now let's approach this problem in a different way. Same exact problem, but let's now take the approach that Chem 101 has you using for a couple of these problems, to put this into a table form. And so let's go ahead and, actually I want to leave the equation here. Okay, so we've erased everything that we had except for the equation. And so let's start setting up a table the same way that Chem 101 had us do. And so the first thing in our table is going to be our initial amount of moles of each of our reactants, or of each of the items in our equation, really. And so we're going to do the same thing that we did before and convert our given amounts to moles. And if we recall, I'm just going to go back to cheat, see what those were. We had 83.2 moles of our silicon dioxide. And we had, what was it, 416.3 moles of our carbon. Now we're not starting with any of the silicon carbide or any of the carbon monoxide. And so now what we need to look for is how much our number of moles are going to change by. And so that's our next step in our table, is looking for our change in moles of each. Now, the important thing to remember here is that our change, since one of these reactants is our limiting reactant, one of them is the excess reactant, we want to look for the change in moles that will give us 0 moles left of one of these reactants. And so, and we have to take into account here as well our ratios from our balanced equation. And so let's start first with maybe assuming that carbon is our limiting reactant. So that would be our reactant that ends up at 0 moles. And so in order for that to change, we would have to have negative 416.3. Now, if we look at what our ratio is, for every 2 carbons that we lose, so for every 2 carbons that we lose, we only lost 1 silicon dioxide. And so if we're going to lose 416.3, that 416.3 carbon, then that would mean that we would have to have lost 208.15. I shouldn't have needed to use a calculator for that, but I did. Again, it's still early in the morning. So I would have had to have lost 208.15 moles of silicon dioxide in order to have lost 416.3 moles of carbon. We can see immediately that doesn't work. I don't have 208.15 moles of silicon dioxide to lose. I only have 83.2 to lose. And so that tells us that carbon cannot be the limiting reactant in this problem. Because in order to use up all the carbon, I would have to use more silicon dioxide than what I actually have. And so that's not going to work for us. So let's go ahead and start fresh. And instead, let's go on an assumption that our silicon dioxide is going to be our limiting reagent. And so we would end up with 0 silicon dioxide left, which means that we would have to lose 83.2 moles of silicon dioxide. Now again, for every mole of silicon dioxide that we lose 2 moles of carbon from our balanced chemical equation. So 83.2 times 2 means that we will have lost 166.4 moles of carbon. Now we could fill out the rest of the table as well. We can see that we have a 1-to-1 ratio between our moles of silicon dioxide, and we're basing everything now off our moles of silicon dioxide because that's our limiting reagent. So we're also going to gain 83.2 moles of silicon carbide, and we're going to gain 166.4 moles of carbon monoxide because we have a 1-to-2 ratio of silicon dioxide to carbon monoxide. And so then we could go ahead and go through and fill out the rest. We're going to have 416.3 minus 166.4. We're going to have 249.9 moles of carbon left. And we're going to end up with 83.2 moles of silicon carbide and 166.4 moles of carbon monoxide. The question ultimately is asking us for our theoretical yield of silicon carbide. So we know that we produce theoretically 83.2 moles of our silicon carbide. And so now we can simply convert that over to grams. I have to look back to see it was 40.0955. And we put that into our calculator. And we see hopefully the same answer we had before. 3.34 times 10 to the third grams of silicon carbide. So it's just another way to approach the problem using these tables rather than comparing our molar ratios in the way that we did before. One thing that I do like about the tables is that, let's say we had a question like in one of the other lecture examples. Let's say we wanted to know the amount of our excess reactant that was left over. So our excess reactant is our carbon. If we want to know the amount of that left over, that's an easy calculation then. We know how many moles we have left of carbon. We can just convert that over to grams, and it's nicely done for us. So that's one of the things that I do really like about setting things up in a table like this, is it provides you with that more extra information that's easy to find at this point. Let's go ahead and walk through another one. So this was a question about DDT, which is an insecticide that's been banned in the US for decades now. But we have instructions on how it's prepared, and we're given an amount of chlorobenzene that we start with. We're given the amount of chloral that we start with, and we're told how much DDT is actually produced in the reaction. And so ultimately, we want to find our percentage yield. In order to find our percentage yield, we need to first find our theoretical yield. We'll find that through doing a limiting reactant problem. And so we need to find our limiting reactant. And so for this question, I'm going to go ahead and use the table problem solving technique. And so we're given the balanced equation now for this one. We don't have to balance it. It is already balanced for us. And so our first step is, let's go ahead and just write that out so we have it. 2C6H5Cl plus C2HOCl3 gives us C14. I'll write that 4 a little bit neater. There we go. C14 H9 Cl5 plus H2O. And so there's our balanced chemical equation. And so the first thing that we're going to calculate is our initial moles. We're told that we have 451 grams of chlorobenzene. And so I'll run those calculations maybe down here. 451 grams of the chlorobenzene, the C6H5Cl. And I looked up the molar mass. That was 112.56. So 451 divided by 112.56 gives me an initial moles of my chlorobenzene of 4.00 moles. And so then, and I won't show the calculation for this, you guys have seen these calculations plenty of times at this point, but we also have our other starting amount, our 368 grams of chloral, divided by the molar mass of that of 147.39. Tells me that I'm starting with 2.50 moles of my chloral. Let's just neaten this up a little bit. Erase our work down here from before. Keep things tidy. Okay. Then we're starting with 0 and 0 of our DDT and our H2O. So then the other items that we need to calculate for this table are our change in moles and our final moles. Now again, remembering that our change has to be whatever gives us 0 of one of our particular reactants. And so we're going to go ahead and analyze that. So let's take a look at what that looks like. So we just sort of pick one to start out and start our analyzing. So let's say if chlorobenzene, the C6H5Cl, if that was our limiting reactant, then we would have a change of -4 moles of that to leave us with 0. Now we have a 1:2 ratio here. For every 2 chlorobenzenes, only 1 of the chloral actually disappears. And so we would have a change of -2 for this reactant, which would leave us with 0.50. And so we can see already this is the correct setup, because this is the one that is going to leave us with some excess of one of the reactants, and the other reactant is 0. Just in case you don't believe that, let's go through and prove it and choose the other one instead, just to show And so let's say that we make an assumption to start that the chloral is our limiting reactant. Now again, looking at our ratio, for every one chloral that disappears, 2 of the chlorobenzenes have to disappear. So if we lose 2.5 moles of the chloral, we would have had to have lost 5 moles of the chlorobenzene, and we don't have those 5 to lose. And so that means that the chloral cannot be our limiting reactant. And so this would be incorrect. And so we know that like I said, that the chlorobenzene is our limiting reactant. We're going to lose 4 and end up with 0. It means that we're going to lose 2 of the chlorals and be left with 0.50. So our limiting reactant is the chlorobenzene. And so we're going to base our amount of products on that. For every one chlorobenzene, for every 2 chlorobenzenes that I lose, I only gain 1 DDT. And so that means that I'm going to end with 2 moles of my DDT, or I'm going to change by an amount of 2 moles of DDT. I'm also going to change by 2 moles of water. And so for my final amounts, I'll have 2.0 moles of DDT and 2.0 moles of water. So now I know which is my limiting. To calculate my theoretical yield, I'm now going to take those 2.0 moles of DDT, multiply that by the molar mass of DDT, which is 354.49. For a final theoretical yield of 708.98 grams of DDT. Now again, that's just our theoretical yield. We're given an actual yield here in our problem of 507 grams. We know to calculate percent yield, I'm going to, and I'll switch to red for that because why not? So my percent yield is going to equal my actual, the 507 grams that I did produce, divided by my theoretical, times 100 to convert to a percent. And so I end up with a percent yield of 71.5%. Let's see if the answer agrees with us. Chlorobenzene limits, my theoretical yield, 709 grams, which is correct. Once we account for sig figs in our answer here, this would be converted to 709. And then our percent yield of 71.5%. And so let's look at the last example that was given in lecture. We want to know the percent yield of ammonia, NH3, if 50 grams of nitrogen and 50 grams of hydrogen react to form 30 grams of ammonia. First step, we need our balanced chemical equation. And so we're told that nitrogen and hydrogen react. We have to remember that both of those are diatomics. So N2 plus H2 react to form our ammonia, NH3. So this is all just given to us in the problem. Now we need to balance this equation. We have 2 nitrogens in our reactant side, only 1 in our product side. So we're going to put a 2 in front of our ammonia. That now gives us 6 hydrogens. We only have 2 on our reactant side. And so a 3 in front of our H2 takes care of that. And so let's use the comparison of molar ratios in order to do this problem. So ultimately, again, let's think about what we're looking for. Ultimately, for our final answer here, we want the percent yield of ammonia. We're given the starting amounts of both of our reactants. We're told how much ammonia actually forms. There's our actual. So what we need to calculate is our theoretical yield. In order to do that, we need to first figure out our limiting reactant and base our answer off that. And so we're going to take the mole ratio comparison approach here. And so we are going to take our 50 grams, 50.0, grams of N2. Convert that over to moles. We're starting with 1.78 moles of N2. We're also told that we start with 50.0 grams of H2 divided by the molar mass of H2. We're starting with 24.80 moles of H2. We can see where this is going pretty quickly already. But let's go ahead and just actually prove it. So again, I usually like to just divide my larger by my smaller, so I end up with a number above 1. So we're going to take our 24.80 moles of H2 divided by 1.78 moles of N2 to give us a molar ratio of what we have. We have 13.9 moles of H2 per every 1 mole of N2. And so again, this is what we actually have in this particular reaction with these particular given starting amounts. What we need, we look back at our balanced chemical equation, we see that we need 3 moles of H2 to every 1 mole of N2. No need to divide that out. That's already per 1 mole. And so this is what we need according to our balanced chemical equation. So again, we can see pretty quickly here that we have much more hydrogen than we actually need. And so hydrogen is in excess. That means that our nitrogen must be our limiting reactant. And so we're going to base everything off that. So let's go ahead, now that we've determined our limiting reactant, let's go ahead and just erase this down here, give us some more room to work. And so we know, and it might help to even just write this in so that we have a record of it and we remember that N2 is our limiting reactant. So we're going to base everything off that. So we know that we have 1.78 moles of N2. We look at our molar ratio, we produce 2 moles of NH3 per every 1 mole of N2 that we start with. 1.78 times 2 means that we're going to produce 3.56 moles of NH3. We can then multiply by the molar mass of NH3, 17 grams of NH3 per every mole of NH3. Means that I'm going to produce 60, or theoretically 60.52 grams of NH3. So again, let's remember what this actually is. This number that we calculate here at the end of a stoichiometry problem. Can't spell theoretical this morning. That is our theoretical yield. We're given an actual amount in this problem. We are told that we actually produce 30 grams of ammonium. We'll divide that by our theoretical, or 60.52, multiply by 100 to convert to a percent. And we're going to call it pretty much right at 50.0% yield. Little difference just in rounding, 49.5. Our theoretical yield of 60.6. Again, that was just probably a difference in how I rounded some molar mass or rounded another number midway through. But that is how we do these. I'm going to just show you one more method of how we would do these problems. let's go ahead and just do this, look at this same exact one. So remember our equation was N2 plus 3 H2s give us 2 NH3s. The final way, or the other way that we can perform limiting reactant problems is simply to carry the whole reaction out using the amounts of both of our given starting materials. And so what I mean by that is, let's start with an amount of, keep it in blue, we had our 50.0 grams of N2 was one of our starting amounts. And so let's see how much NH3 we could theoretically make based just on the 50 grams of N2. So our 50 grams of N2, first we have to convert it to moles of N2. And so 1 mole of N2 for every 28.02 grams of N2. Then we use our molar ratio to convert to moles of NH3. 2 moles of NH3 to every 1 mole of N2, and then finally to grams of NH3. And so we do this out. Should pretty much be what we had before, the 60.6, 60.5, 60.67. So based on starting with 50 grams of N2, I can form 60.67 grams of NH3. Now let's do the same calculation, but instead based on starting with 50.0 grams of H2. So we're going to do the same thing. We're going to convert H2 to moles. 1 mole of H2 to every 2.016 grams of H2. We have 2. We create 2 moles of NH3 per every 3 moles of H2, just from our balanced chemical equation. Finally, convert over to grams of NH3. And so we do this calculation out. Times 2 divided by 3 times 17. And we get 281 grams of NH3. So based on starting with 50 grams of hydrogen, I could form 281 grams of NH3. But I know I can't make 281 grams of NH3. I only have enough nitrogen to make 60.67 grams of NH3. And so that tells me that nitrogen has to be my limiting reagent. And it also tells me that this is going to be my theoretical yield. So again, it's just another way to approach this. Instead of doing the table, or instead of doing a comparison of your molar ratios, you could simply carry the whole question out for both reactants. Whichever one forms the least amount, there's your limiting reactant. And so those are several examples. Again, I really hope that you worked through these on your own before watching this. But we've looked at several different ways now to approach limiting reactant problems. There's no right or wrong way. Any of these methods will get you to the correct answer. It's just get comfortable with whatever method works for you. And I hope this was helpful. And as always, if you have any questions, feel free to get in touch and we can go over some. Set an appointment with a tutor at the Learning Commons. You can go through some of these problems, whatever works for you, in order to get some help if you need it. But yeah, I do hope this was helpful, and thanks for watching.